Based on the carrier statistics, we may calculate the reverse bias current by counting the amount of charges passing through a particular location per unit time. To do this, we have to find a location to count the number of carriers passing by. It can be anywhere along the path that the current flows. But it would be much easier to count at the location with the lowest carrier concentration. It is just like if you want to measure the rate of water flow in a river, you would prefer to measure it at the narrow part of the river. By examining the electron concentrations, the location with the lowest electron concentrations is in the p-psi neutral regions near the edge of the depletion region. And the driving force for electron motion at this location is mainly diffusion. To calculate current density or current per unit area due to diffusion, we have a simple relationship given by Jn equal to Q dn over dx. dn over dx in the equation simply means the rate of carrier flow is proportional to the difference in electron concentration. When the difference of electron concentration in two regions is large, dn over dx will also be large, resulting in a larger carrier flow. In the equation, dn is the electron diffusion coefficient, and its values indicates how mobile electrons are in the medium. It can be regarded as a constant once the medium is known. To calculate the current density, the number of electrons flowing has to be multiplied by Q, which is the charge that each electron carries. The corresponding diffusion current density for hole will be Q dp over dx, with the hole concentration denoted by P and the hole diffusion coefficient denoted by dp. In the graph showing the electron concentration along the p-n junction, dn over dx is just the slope of the electron concentration of the p-psi neutral region at the edge of the depletion region. We can draw a straight line to represent this slope. Let's label the electron concentration at the edge of the depletion NPD, indicating the electron concentration on the p-psi near the depletion region. NPD is not a constant, but a variable which depends on the voltage across the junction. Let's also label the distance that the straight line cut the equilibrium concentration by Ln. It turns out that Ln corresponds to the diffusion length of electrons, and it represents the average distance an electron can travel before it recombines. This will be explained in more detail later. At this stage, you may assume it is just another known constant. With all these new symbols defined, the slope of dn over dx for the p-psi electron near the depletion region is just NPD minus NP0 divided by Ln. And the electron diffusion current density is just this value multiplied by Q dn. In this equation, all are constants with respect to the applied voltage, and the only unknown is NPD.